Good morning, all. We will talk about one of the logics used in the digital world, which is called the Diode Transistor Logic. Basically, the name itself implies that there will be a diode associated, there will be a transistor logic, and they combine together to form called the diode transistor logic. So we will get into the details straight away. So the diode transistor logic, basically, if you see, came into picture based on the different disadvantages that are seen with the previous logic families like the RTL resistor transistor logic. So now we will jump straight away into the diode transistor logic circuit. So basically, diode transistor logic circuit is comprising of three sections, we should say. One is diode section, where there will be a diodes associated with it, and second one will be a level shifter section. There will be a level shifter section associated, and then comes the transistor section. So these three together form the diode transistor logic. So basically, with the diode, with the digital logics, we know that we can form different logical gates, especially the NAND and the NOR gates, right? So with the diode transistor logic, using the first diodes, we will see how to form a NAND gate and a NOR gate. Okay, for a NOR gate, the logic would be this way, where there is a input A, signal B, and when either of these signals are high, that means because there is a diode, if you give some voltage here which is greater than 0.7 volt, example, let us assume the breakdown of the voltage is 0.7, any voltage greater than 0.7 voltage here on A gets the diode into forward bias condition, and then this voltage will be seen here. This voltage minus 0.7 volt will be seen here, that means it is high. So what it means is, any input which is high, if any input is high, then that means you see a voltage here. If both the voltages are 0, it meant you see that the output is 0, because the diodes will still be in reverse bias condition. There is one more condition where the diodes can be used. This is A, this is B, and if you have a power supply here, okay, now let us assume we give a power supply 5 volts or 3.3 volts based on the logic condition. Now here, if you give a voltage of if you give 0 0 here, example, okay, 0 means this diode, on the negative side of the diode there is a low voltage, on the positive side of the diode there is a high voltage because of this rail. That means this diode is forward biased. When this diode is forward biased, we know that the voltage across this would be 0.7 volt, the voltage drop across this diode. So now, irrespective, if once this becomes 0, irrespective of other diode state, this 0.7 voltage will be maintained, because the lower voltage always gets the preference. So now that means if any of the input among these is 0, the output goes to 0. So if you take the truth table, 0 0 0 1 1 0 1 1, okay, so this will be 0, right, and then this is 0, this is 0, and only when both the inputs are 1, this will become 1, right? So that is how this works. So these are the simple input diode configurations which are used in a diode transistor logic. So now here one more small point is if you see here the OR gate or the AND gate functionality which we are seeing here basically is the major input section of the diode transistor logic. So if you want to understand this, one thing what you need to know is basically you need to know the diode characteristics. Okay, diode characteristics if you draw basically would be this way, where there will be a breakdown voltage beyond which the diode starts conducting and the voltage gets clamped at that point. And on the reverse bias side, if the voltage on the cathode side of the diode exceeds the voltage beyond that breakdown, again the diode breaks down and suddenly starts conducting lot of current. So these characteristics is what you need to know initially. Now let us go to the second section. The second section basically is the level shifter section which we have been talking. So for now we will consider the AND gate condition which we have seen, where you have A, you have B, and then there is a pull up here. So here you will have something called the level shifter. So the level shifter could be a simple resistor or the level shifter could be a diode. So we will take a simple resistor for our easy understanding, and then this will be the output. Okay, now let us see how this operates. So this, if you say R1, R2, R3 plus VCC. Okay, so now here when there is particular voltage here, right? Example, let us assume this is VCC, this is V1 is the voltage that is coming here. The only condition when voltage comes here is when both the diodes are high. That means 1 which is equal to VCC. So in this condition only V1 comes here. When V1 comes here, you can see here V1 sees a resistive divider here. Okay, because this voltage, we need to know the voltage here, which is nothing but the V out now. So V out is nothing but V1 into R3. R3 is nothing but this voltage by R2 plus R3. Okay, that means there is a level shifting that is happening here. This level shifting can be done by diodes as well, because if the resistors are considered to be consuming power, we can have diodes in place of resistors, or a Schottky diode here, where it improves the speed of the operation. And then now this is the first stage which we talked in the diode section, and there is a second stage. Now the third stage is nothing but this. If you take R4 and plus VCC, again the same voltage, this is nothing but a CE configuration, common emitter configuration. So now the last stage of this is a common emitter configuration where it acts as an inverter. Okay, now we said this is a AND gate, this is a level shifter, this is an inverter. Now AND gate with a level shifter doesn't happen anything except that there is a voltage variation, and when this input is inverted, you get a NAND gate. AND inverted NAND, right? Because this is AND gate, and when you invert this becomes a NAND gate. So now this entire DTL logic operates as a NAND gate. Similarly for the NOR gate. So this is how a DTL logic operates, or this is the basic circuit of the DTL logic. So one of the major advantage, if you see here, basically is you can increase the number of inputs as per your need, so that this voltage rail doesn't get loaded. So you can increase these voltage rails. That is one of the advantage. That means you are increasing the fan in. And the second thing is there is less power dissipation that is seen here. And one major disadvantage that we can say is by the time we apply here, because of all these stages, there will be a like a propagation delay that is associated. So one of the major disadvantage we can say is that the diode transistor logic has a high propagation delay. Now there are ways to achieve this. One of the major reason why this has a high propagation delay is this particular transistor you see here. When you drive this voltage on the base, the collector current gets driven, and this drives this particular transistor into saturation state. It turns on and it goes into the saturation state. So to again cut off this transistor and operate in a different, like the opposite of on is off, right? So to bring it into a off condition, you need some time for this to get cut off from the on condition. So that delay adds up. So there are different ways that designers use this, where they employ a Schottky based diode by taking the base voltage, the collector voltage, and fed back to the base, so that you don't drive this into the saturation state and still the common emitter inverter functionality is maintained. So there are different ways. So you can see here, one advantage is that when you require more number of inputs for this logic functionality, you require this DTL. But propagation delays, still power consumption wise, we don't say it's too much improvement, but still there is a power loss here associated because of these diodes, resistors. And one more major point is the noise immunity. The noise immunity of the diode transistor logic is okay compared to the other logic families previously we have seen. So the noise immunity is nothing but it is one of the characteristic of these logic families, where the performance of the logic family under a noisy condition is determined. So that is one thing. And this basically diode transistor logic is used in some of the conditions where you need to take a decision based on the different inputs that are coming in. So this is the basic introduction. Please let us know if you have any comments. Thanks for watching.